How can we regenerate the Earth completely, build the most sustainable society and eventually terraform new worlds by using underground fungal networks? This is the most profound synthesis question of our entire conversation, the moment where the smallest living thread in the soil becomes the foundation of a cosmic civilizational strategy. Fungal networks are not merely biological curiosities. They are the original internet, the original circular economy, the original planetary management system, and they may be the key to everything we have discussed across this entire conversation. The foundational vision. Why fungi are the master key. Before building the vision, we must understand what fungal networks actually are at the deepest level, because their true nature is far more extraordinary than popular understanding suggests. Fungal mycelium, the thread-like vegetative body of fungi that forms networks through soil, is not simply a passive pipeline for nutrients. It is an active, intelligent, distributed living system that performs functions no other organism on Earth performs, across scales from the nanometer to the continental. At the molecular scale, fungal enzymes break chemical bonds that nothing else can break, the lignin polymer that locks carbon in wood, the silicate minerals that lock nutrients in rock, the xenobiotic compounds that industrial civilization has deposited in soils. Fungi are the ultimate chemists, performing reactions at ambient temperature and pressure that industrial chemistry requires extreme conditions to replicate. At the cellular scale, individual fungal hyphae, threads 1 to 10 micrometers in diameter, navigate through soil with a form of intelligence, responding to chemical gradients, physical obstacles, moisture, temperature, and electrical signals to find and exploit resources with extraordinary efficiency. The hyphal tip is simultaneously a sensing organ, a decision-making unit, and an actuator, integrating information and adjusting growth direction in real time. At the network scale, connected hyphae form structures of extraordinary complexity, anastomosing networks that create redundant pathways, preferentially routing resources through high conductance channels while maintaining backup routes, reorganizing dynamically in response to changing conditions. The network topology of mature mycelium resembles, in its mathematical structure, both the internet and the neural networks of animal brains, not by coincidence but because all three are solutions to the same optimization problem: how to route information and resources through a distributed system with maximum efficiency and resilience. At the ecosystem scale, mycorrhizal networks connect virtually all plants in a forest community into a single integrated system, sharing carbon, water, nutrients, and chemical signals across hectares, mediating competition and cooperation between plant species, and regulating the productivity and resilience of the entire community. The forest is not a collection of individual trees. It is a single superorganism, and the fungal network is its nervous system. At the planetary scale, fungi have been the primary regulators of the global carbon cycle, the nitrogen cycle, the phosphorus cycle, and the weathering of rock to soil for at least 450 million years. The terrestrial biosphere as we know it, the soils, the forests, the grasslands, the agricultural lands that feed humanity, exist because fungi built it, maintain it, and continue to regulate it. Without fungi, the land surface of Earth would be bare rock and mineral dust. This is the system we are going to use to regenerate Earth, build a sustainable civilization, and terraform other worlds. Understanding the network deeply. The true architecture of fungal intelligence. Chemical communication. Fungal networks communicate through chemistry with a sophistication that rivals the endocrine system of animals. Hyphae release and detect hundreds of different chemical compounds, volatile organic compounds that signal through air, dissolved compounds that signal through water films, and contact chemicals that signal through direct hyphal contact. When a fungal network encounters a resource, a dead tree, a nitrogen-rich patch of soil, a living plant root, it releases specific chemical signals that propagate through the network, attracting hyphal growth toward the resource and recruiting specialized enzyme-producing hyphae from throughout the network. The response is coordinated across the entire network, not just in the vicinity of the resource, demonstrating a form of information integration that operates at the scale of the entire network simultaneously. When a fungal network encounters a threat, a competing fungal species, a pathogen, a physical disruption, it releases alarm compounds that trigger defensive responses throughout the network, the production of antifungal compounds, the withdrawal of cytoplasm from threatened hyphae, and the reinforcement of alternative pathways around the disrupted zone. The network is not just connected, it is aware, at the network level, of what is happening at every point within it. Electrical signaling. Beyond chemical communication, fungal networks transmit electrical signals, action potential-like voltage pulses that propagate along hyphae at speeds of millimeters to centimeters per minute. These electrical signals appear to encode information about environmental conditions, resource locations, and network state, propagating across the network much faster than chemical diffusion allows. The electrical signals of fungal networks share mathematical properties with neural action potentials. They have threshold-dependent firing, refractory periods, and frequency-encoded information content. The analogy to neural signaling is not superficial. Both systems are solutions to the same problem: how to rapidly communicate information across a spatially extended network using living tissue as the transmission medium. Memory and learning. Most remarkably, fungal networks appear to exhibit a form of memory, the ability to retain information about past experiences and modify future behavior accordingly. Networks that have previously been exposed to a particular resource pattern respond more quickly and efficiently when exposed to the same pattern again. Networks that have experienced disruption at a particular point develop stronger redundant pathways around that point, even before further disruption occurs. This network memory is not stored in any single location. Like the distributed memory of a neural network, it is encoded in the strength and topology of network connections throughout the mycelium. It is a form of structural learning, experience-modifying network architecture in ways that improve future performance, that represents a biological precursor to the learning algorithms of artificial neural networks. Regenerating Earth through fungal networks. Phase 1. Soil restoration at continental scale. The soil crisis and the fungal solution. Global soils have lost between 50 and 70% of their original carbon content since the beginning of agriculture, carbon that has entered the atmosphere as CO2, contributing to climate change, and left soils degraded, infertile, and vulnerable to erosion. Restoring this lost soil carbon, rebuilding the living, fungal-rich soils that supported pre-agricultural ecosystems, is simultaneously the most powerful carbon drawdown strategy available in the foundation of long-term agricultural sustainability. The key to soil carbon restoration is fungi, specifically the glomalin protein produced by arbuscular mycorrhizal fungi. Glomalin is one of the most abundant proteins in soil, constituting up to 30% of soil organic carbon in healthy systems. It is extraordinarily stable, persisting in soil for decades to centuries, and it is the primary agent responsible for building and maintaining soil aggregates, the crumb-like structures that give healthy soil its characteristic texture, water retention, and gas exchange properties. Every time industrial agriculture tills soil, applies synthetic fungicides, or eliminates the diversity of soil organisms through monoculture, it destroys the glomalin-producing mycorrhizal network. Rebuilding it is the foundation of soil restoration. Continental Scale Mycorrhizal Restoration Program. A systematic program to restore mycorrhizal networks across degraded agricultural and post-industrial lands would proceed through 5 integrated stages. Stage 1. Network mapping. A comprehensive survey of existing mycorrhizal network remnants, using environmental DNA sequencing of soil samples, ethnometabolic coding to identify fungal species, and electrical resistance tomography to map network extent, identifies the surviving network fragments from which restoration can propagate. Like mapping the remnants of a forest after logging, this survey identifies the biological seed from which recovery can grow. Stage 2. Pioneer network establishment. In the most severely degraded soils, where mycorrhizal networks have been completely eliminated, pioneer fungal communities must be established from scratch. Biochar application creates the physical habitat that pioneer fungi need, the porous, carbon-rich matrix that provides shelter, moisture retention, and the chemical environment that mycorrhizal and arbuscular mycorrhizal species require. Precision microbial inoculants. Communities of pioneer bacteria and fungi formulated for specific soil types and climates are co-applied with the biochar, seeding the biological community that will develop into a functional network. Stage 3. Host plant network. Mycorrhizal fungi cannot exist without plant hosts. They are obligate symbionts that depend on plant photosynthesis for their carbon supply. Establishing mycorrhizal networks requires simultaneously establishing host plant communities. Cover crop mixtures of mycorrhizal host species, grasses, legumes, herbs, and tap-rooted plants, provide the diversity of root architectures and exudate chemistries that support high-diversity fungal communities. These cover crops are the nurse plants of the fungal restoration, protecting and feeding the growing network through its establishment phase. Stage 4. Network expansion. Once established, mycorrhizal networks expand naturally, but expansion can be dramatically accelerated by management practices that favor network development. Eliminating tillage removes the primary physical disruption. Eliminating synthetic fungicides removes the primary chemical disruption. Maintaining continuous living root cover, never leaving soils bare, maintains the photosynthetic supply that feeds the network year-round. Introducing diverse plant communities, intercropping, agroforestry, silvopasture, provides the diversity of fungal habitats and host preferences that support the highest diversity, most functionally complete networks. Stage 5. Network intelligence integration. As networks develop, connecting them to the omega tree system and the planetary intelligence network described in previous sections creates a monitored, managed biological system that can be optimized at continental scale. Soil sensors monitoring network electrical activity, atmospheric monitoring of CO2 and water vapor exchange, satellite monitoring of vegetation productivity, all feed into the global material flow intelligence system, providing real-time data on the progress of soil restoration and the functioning of restored networks. quantifying the carbon potential. A fully restored global mycorrhizal network, supporting healthy soils across the approximately 5 billion hectares of agricultural integrated land that currently have diminished fungal communities, could sequester between 1 and 3 gigatons of carbon per year in soil organic matter, primarily as glomalin and associated microbial biomass. Over a century, this represents 100 to 300 gigatons of carbon removed from the atmosphere, comparable to the total carbon emitted by human civilization in the past several decades. This is not the carbon stored in above-ground vegetation, it is carbon stored in soil, where it is far more stable and far less vulnerable to re-release through fire, drought, or deforestation. Healthy mycorrhizal soils represent a carbon store that can persist for millennia if managed appropriately, a geological-scale carbon sink created by biological processes operating at agricultural scale. Phase 2. Forest regeneration through network-guided succession. The network is forest architect. Natural forest regeneration is guided by mycorrhizal networks. The existing network in a forest fragment colonizes adjacent degraded land through hyphal extension, connecting pioneer tree seedlings to the established network and providing them with the carbon, water, and nutrient support needed to establish in challenging conditions. The network literally pulls the forest across the landscape. The oldest trees in the network, through their connections to all younger trees, effectively subsidize the establishment of new generations. Harnessing this network-guided succession for large-scale forest restoration requires working with the network's own logic rather than against it. Network-first restoration approach. Conventional forest restoration plants trees first and hopes the fungal community develops. The network-first approach establishes the fungal network first and lets it guide tree establishment, dramatically improving restoration success rates because trees are established into a supportive network community rather than into biologically impoverished soil. The network-first approach begins with establishing diverse mycorrhizal networks in restoration areas using the staged approach described above. Once the network is established, pioneer tree species that form particularly strong mycorrhizal associations, birch, pine, alder, in temperate systems, cecropia, pioneer ficus, leguminous trees in tropical systems, are planted at strategic locations, connecting to the existing network immediately upon root development. These pioneer trees, supported by the established network, grow far faster than conventionally planted trees, receiving carbon subsidies through the network from established plants in adjacent areas, accessing water from deeper in the soil profile through the network's extended reach, and benefiting from the microbial communities that the established network has already built. Studies of network-connected seedlings versus isolated seedlings show growth rate differences of 2 to 5 times, a dramatic demonstration of the support that network connectivity provides. As pioneer trees mature, they feed carbon into the network that supports the establishment of longer-lived late successional species in their shade: oak, beech, maple, hickory in temperate systems, mahogany, Brazil nut, emergent dipterocarps in tropical systems. The succession is guided by the network, which distributes resources to the species and individuals best placed to capture them, driving the forest toward its climax state far faster than unmanaged succession achieves. Connecting fragmented forests. One of the most critical applications of fungal network management is the reconnection of fragmented forest patches, isolated remnants separated by agricultural land, urban areas, or other barriers that prevent the natural spread of mycorrhizal networks. Forest fragments with severed mycorrhizal connections are biologically isolated. Their tree communities cannot receive support from or provide support to adjacent fragments, reducing their resilience and long-term viability. Reconnecting these fragments through mycorrhizal corridors, strips of land managed to allow fungal network development between fragments, restores biological connectivity at the landscape scale. Mycorrhizal corridors can be established in hedgerows, riparian buffer strips, road verges, and field margins, linear features that cross agricultural landscapes and connect forest patches. Their width need be only a few meters for fungal connectivity, while providing far greater biodiversity value than the same land in conventional agricultural use. A global program of mycorrhizal corridor establishment could reconnect the fragmented forest landscapes of Europe, North America, Southeast Asia, and Africa, restoring the landscape-scale ecological function that fragmentation has eliminated. Phase 3. Water cycle restoration through fungal hydrology. How fungal networks control water. The relationship between mycorrhizal networks and water cycles is far more profound than is commonly appreciated. Fungal networks are not just passive conduits for water, they are active hydrological managers that regulate water flow through soils at multiple scales. Soil structure and infiltration. The glomalin produced by mycorrhizal fungi is the primary agent responsible for creating and maintaining the aggregate structure of healthy soils. Soil aggregates, crumbs of mineral particles bound together by glomalin and other organic glues, create the macropores that allow rapid water infiltration. In a healthy mycorrhizal soil, rainfall infiltrates rapidly and moves deep into the soil profile, recharging groundwater rather than running off the surface. In a degraded, fungally depleted soil, the aggregate structure collapses, macropores close, infiltration slows dramatically, and rainfall runs off the surface, carrying topsoil with it and failing to recharge groundwater. The difference between a fungal-rich and a fungal-depleted soil in terms of water infiltration can be an order of magnitude. The same rainfall event that soaks into a healthy soil and recharges the water table becomes a damaging flood event on degraded land. Restoring mycorrhizal networks across watersheds therefore directly restores the hydrological function of those watersheds, increasing rainfall infiltration, reducing flood peaks, extending the period of groundwater-fed streamflow through dry seasons, and recharging depleted aquifers. The restoration of Earth's water cycles begins in the soil, and specifically in the fungal networks that build the soil structure that manages water. Hydraulic redistribution. Mycorrhizal networks participate in hydraulic redistribution, the movement of water from wet to dry zones through the network, driven by water potential gradients. At night, when atmospheric demand for water is low, water moves from moist deep soil through mycorrhizal hyphae to dry surface soil, raising surface soil moisture and benefiting shallow-rooted plants and surface organisms. This process, documented in numerous ecosystems, represents the network functioning as an active water distribution system, moving water from where it is plentiful to where it is needed. At landscape scale, hydraulic redistribution through connected mycorrhizal networks can move significant quantities of water across gradients of soil moisture, from riparian zones and valley bottoms where water is abundant to ridge tops and dry slopes where it is limiting, creating a more equitable distribution of water across the landscape that supports higher plant productivity and diversity than moisture gradients alone would permit. Continental water cycle restoration, a program to restore fungal networks across degraded watersheds globally would, over decades to centuries, restore the continental water cycles that industrial land use has disrupted. Increased rainfall infiltration across restored agricultural lands would recharge depleted aquifers, with water tables rising across regions that have experienced generations of groundwater depletion. Restored streamflow timing would reduce both flood and drought extremes, floods reduced by increased infiltration, droughts reduced by increased groundwater contribution to streamflow during dry periods. The most dramatic water cycle restoration potential lies in the great agricultural regions of the world, the Great Plains, the North China Plain, the Indo-Gangetic Plain, the Cerrado of Brazil, where decades of intensive cultivation have depleted aquifers and degraded soil structure, replacing the original mycorrhizal-rich soils with biologically impoverished monoculture systems. Restoring mycorrhizal networks across these landscapes would not just restore soil carbon, it would restore the hydrological infrastructure that made these landscapes productive in the first place. Phase 4, Atmospheric Restoration through Biological Networks. The fungal carbon pump. Mycorrhizal networks are one of the most significant biological carbon pumps on Earth, transferring carbon from the atmosphere to long-term soil storage at a rate that rivals photosynthesis in its planetary significance. Recent research estimates that mycorrhizal networks globally transfer between 5 and 13 gigatons of carbon per year from plant photosynthesis to soil, representing 5 to 10% of total atmospheric CO2, and that a significant fraction of this carbon enters long-lived soil organic matter pools that store it for decades to centuries. This carbon pump has been severely impaired by industrial agriculture and land use change. Restoring it, by restoring the mycorrhizal networks and host plant communities that drive it, represents the largest available biological carbon sequestration opportunity. The Mycorrhizal Carbon Sequestration Program, a systematic global program to restore mycorrhizal carbon pumping across degraded lands, would operate through 3 parallel streams. Agricultural lands, covering approximately 1.5 billion hectares globally, transition from conventional to mycorrhizal supportive management, cover cropping, reduced tillage, diverse crop rotations, and integrated agroforestry all support mycorrhizal network development and carbon sequestration. Conservative estimates suggest that mycorrhizal restoration across global agricultural lands could sequester 0.9 to 1.85 gigatons of carbon per year, comparable to the annual emissions of the entire global aviation and shipping industries combined. Degraded lands, approximately 2 billion hectares of former agricultural, mining, and deforested land with severely impaired mycorrhizal communities, restored through the network-first approach, establishing fungal communities as the foundation for ecosystem recovery. These lands have enormous carbon sequestration potential precisely because they have lost so much of their original soil carbon. Restoring fungal networks initiates a decades-long process of soil carbon rebuilding that collectively represents a massive carbon sink, assisted natural regeneration on abandoned agricultural lands, supporting the natural recovery of native vegetation by establishing mycorrhizal networks that guide plant succession, is the highest leverage, lowest cost intervention available. Nature wants to regenerate, the mycorrhizal network gives it the infrastructure to do so rapidly and effectively, building the most sustainable society. The fungal economy. Biological manufacturing through fungal systems. The most sustainable industrial system conceivable is one that uses living organisms, specifically fungal systems, as its primary manufacturing platform, because fungi achieve what no industrial process can, the transformation of simple, abundant, locally available materials into complex, high-value products using only ambient temperature, ambient pressure, and biological energy, with no toxic byproducts and with product structures that are fully biodegradable and recyclable. The mycelium material economy. A society built on mycelium materials manufactures its physical artifacts, packaging, insulation, building panels, furniture, textiles, electronic substrates, from fungal growth on agricultural waste. The manufacturing process is biological and therefore inherently circular. The same substrate that grows mycelium composites can, at end of product life, be reinoculated to grow new products, or composted to return nutrients to agricultural soil, feeding the plants that produce the agricultural waste that feeds the next product generation. The manufacturing infrastructure for a mycelium material economy is distributed, low energy, and low capital. A growing room, an autoclave for substrate sterilization, a drying oven, and a mold for shaping are the core requirements. This infrastructure is accessible to communities at any scale, in any location, using locally available agricultural residues as feedstock, democratizing manufacturing in a way that centralized industrial systems cannot. Products manufactured from mycelium composites include structural insulation panels for building construction, replacing petroleum-based foam insulation, packaging materials of any shape and density, replacing expanded polystyrene, leather alternatives for fashion and upholstery, replacing animal leather, acoustic dampening materials for construction and transportation, and electronic device housings, replacing petroleum-derived engineering plastics. Fungal food systems. The fungal food economy extends beyond mushrooms to include the full range of nutritional products that fungal systems can produce. Precision fermentation, using engineered yeast and fungal strains, produces proteins, fats, vitamins, and other nutrients from simple sugar feedstocks. Tempeh fermentation, using Rhizopus oligosporus to bind and partially digest legume, grain, and seed substrates, produces protein-rich foods of extraordinary nutritional value with minimal processing energy. Fungal pharmaceutical and chemical industries. The pharmaceutical and fine chemical industries of a sustainable society are based on fungal biosynthesis, using the extraordinary chemical diversity of fungal secondary metabolite pathways to produce medicines, fragrances, flavors, dyes, and industrial chemicals that currently require synthetic chemistry. Penicillin, the first antibiotic, was a fungal product. Statins, the most widely prescribed cholesterol medications, are fungal products. Cyclosporine, the immunosuppressant that made organ transplantation possible, is a fungal product. The fraction of pharmaceuticals discovered from fungal sources that has been commercially developed is tiny compared to what remains undiscovered in the vast chemical diversity of the fungal kingdom. A systematic program to characterize the chemical diversity of the global fungal kingdom, currently estimated to include between 2 and 4 million species, of which fewer than 150,000 have been described and fewer than 10,000 have been examined for bioactive compounds, would reveal pharmaceutical and industrial chemical resources of incalculable value. These compounds could be produced at industrial scale through fermentation, using the same precision fermentation platforms that produce food proteins. The fungal energy economy. Fungal fuel production. Fungi produce a range of fermentable sugars and lipids from lignocellulosic biomass, the woody structural material of plants that conventional fermentation cannot effectively process. White rot fungi, Phanerotroid chrysosporium and related species, selectively degrade lignin while leaving cellulose and hemicellulose intact, effectively pre-treating biomass for subsequent fermentation to ethanol, butanol, or other fuels without the chemical or thermal pre-treatment that conventional biofuel processes require. A fungal pre-treatment step inserted at the front of the biofuel production process, allowing white rot fungi to colonize and partially degrade agricultural residues, forestry waste, or purpose-grown energy crops before fermentation, dramatically reduces the energy input required for biofuel production and increases the yield of fermentable sugars. The fungal pre-treatment step itself produces valuable co-products, enzyme preparations that can be sold for industrial applications, spent fungal biomass that serves as soil amendment, and partially degraded lignin that can be converted to aromatic chemicals. Fungal electricity generation. Bioelectrochemical systems, microbial fuel cells and microbial electrosynthesis cells, that use the metabolic activity of electrochemically active fungi and bacteria to generate electricity, are a long-term frontier of biological energy technology. Certain fungi, including white rot species, transfer electrons to external electrodes during the oxidation of organic compounds, generating electrical currents as a direct product of their metabolism. A fungal bioelectrochemical system embedded in agricultural soil, using the omega tree's bioelectrochemical root network as its physical infrastructure, could generate distributed electricity from the organic matter decomposition that the fungal network performs naturally, converting what is currently a purely biological process into a combined biological electrical one that produces both the ecological services of organic matter decomposition and electrical power simultaneously. The fungal information economy. Biological computing networks. The intelligence architecture of the omega tree, distributed biological computing nodes communicating through the mycorrhizal network, forms the foundation of a biological internet, a planet-spanning information network that uses living organisms rather than silicon electronics as its computational and communication substrate. A biological internet based on fungal network communication has properties that silicon-based networks cannot replicate. It is self-repairing. Damaged connections are regrown rather than replaced. It is self-powering. The network derives its energy from the organic matter in soil rather than from external power supplies. It is continuously evolving. The network architecture adapts to changing information and resource flow patterns over time, and it is inherently integrated with the biological and physical systems it monitors. The network is not separate from the ecosystem it monitors but part of it, embedded in the same soil, connected to the same plants, responsive to the same environmental conditions. This biological internet complements rather than replaces silicon-based information technology. Its strengths: distributed intelligence, self-organization, long-term operation without maintenance, and deep integration with biological systems, complement the strengths of silicon networks: speed, precision, and programmability, creating a hybrid information infrastructure far more capable and sustainable than either alone. Terraforming new worlds with fungal networks. The fungal terraforming strategy. Why fungi first? Of all the possible approaches to biological terraforming, seeding a planet with cyanobacteria, deploying engineered extremophiles, establishing pioneer plant communities, the most powerful and most fundamental strategy is fungi first. Fungi are the reason that life colonized the land on Earth. The earliest land plants, approximately 450 million years ago, were able to survive on bare rock only because they formed symbiotic associations with mycorrhizal fungi that provided them with mineral nutrients in exchange for photosynthesis. Without the fungal network, the transition from aquatic to terrestrial life might never have occurred, or might have been delayed by hundreds of millions of years. On any planet where terrestrial biological terraforming is attempted, the same logic applies. Plants cannot establish and bear mineral substrate without mycorrhizal support. Soils cannot form without the enzymatic activity of fungal decomposers. The complex food webs that support animal life cannot develop without the fungal decomposer base that processes dead organic matter and returns nutrients to the plant available pool. Fungi are not one component of the biological terraforming strategy, they are the infrastructure on which all other biological terraforming depends. Mars fungal terraforming, the full strategy. Stage 0, Earth preparation. Before any fungi reach Mars, decades of preparation on Earth are required. The preparation involves comprehensive characterization of Earth's fungal diversity, identifying the full range of species, metabolic capabilities, and environmental tolerances available in the fungal kingdom. Of particular interest are extremophile fungi, species that naturally survive conditions approaching Martian surface parameters, extreme cold, low pressure, higher radiation, and chemical stress. The most radiation-resistant fungi known, Platysporium sphaerospermum and Cryptococcus natans, found growing on the walls of the Chernobyl nuclear reactor, use melanin pigments not just to protect their DNA from radiation damage, but to convert ionizing radiation to chemical energy through radiosynthesis. These organisms actively harvest the energy of ionizing radiation for metabolic use, a capability that makes them uniquely suited to the higher radiation environment of the Martian surface. Genetic engineering of candidate fungal species for enhanced Martian tolerance, using every tool of synthetic biology, directed evolution, and CRISPR genome editing, produces strains with combined tolerances that no natural species possesses. A Martian pioneer fungal strain might combine the radiation tolerance of Cladosporium with the freeze tolerance of Antarctic Dothydium with the desiccation tolerance of Xanthoria peridina with the perchlorate tolerance of Deinococcus radiodurans with the rock-dissolving mineral weathering capability of lithobiotic endolithic fungi from desert varnish communities. Stage 1, Lithobiotic Foundation. The first fungal colonizers of the Martian surface are not soil-dwelling species but lithobians, rock-dwelling organisms that live within the pores of rocks, sheltered from surface UV radiation and temperature extremes by the rock matrix, while accessing sunlight filtered through translucent mineral surfaces. Endolithic fungi, species that naturally colonize the interior of transparent rocks like quartz and translucent feldspars, are the ultimate terrestrial analogs for early Martian colonizers. In Antarctic dry valleys and Atacama desert surfaces, these organisms form complete miniature ecosystems within rock pores, photosynthesizing cyanobacteria and algae in the illuminated outer zone, with heterotrophic fungi and bacteria in the darker inner zones, processing the organic matter produced by the photosynthesizers. On Mars, lithobiotic communities deployed within appropriate rock types, particularly in equatorial regions where diurnal temperature swings are moderated within the rock mass, could establish the first biological foothold. The fungi within these communities begin the weathering processes that will eventually create soil, dissolving mineral surfaces with organic acids, chelating metal ions from mineral lattices, and beginning the accumulation of organic matter within rock pores. The timeline for this stage is long, decades to centuries of lithobiotic establishment before surface soil conditions are significantly modified. But the biological seed is planted, and the network begins its work. Stage 2, regolith network establishment. As lithobiotic communities produce increasing quantities of organic matter, carried by wind and meltwater to sheltered surface locations, the first pioneers of regolith-based fungal communities can establish. The regolith of Mars presents extraordinary challenges: no organic matter, toxic perchlorate salts at concentrations fatal to most organisms, extreme pH variability, physical disruption by wind, and intense cosmic radiation at the surface. Engineered pioneer fungal strains address each of these challenges specifically. Perchlorate-reducing fungi, engineered with the perchlorate reductase enzyme pathways from soil bacteria, metabolize perchlorate as an electron acceptor, simultaneously detoxifying the regolith and generating energy for their own maintenance. Melanin-producing strains harvest the abundant UV and ionizing radiation as an energy source, supplementing whatever organic matter is available from lithobiotic communities. Hyphal networks stabilize regolith particles against wind erosion, the same function that fungal hyphae perform in sand dune stabilization on Earth, creating physical stability that protects developing microbial communities. The mineral weathering capability of pioneer fungi begins the soil formation process. Organic acids secreted by hyphal tips dissolve the mineral surfaces of regolith particles, releasing plant-available phosphorus, potassium, calcium, magnesium, and iron. The oxidized iron minerals that give Mars its red color, iron oxides, are reduced by iron-reducing bacteria in the anaerobic zones beneath fungal mats, converting them to more plant-available ferrous forms and changing the surface color from red toward brown as organic matter accumulates. Stage 3, mycorrhizal network for pioneer plants. When the pioneer fungal network has built sufficient organic matter, perhaps 1 to 5% soil organic carbon in protected surface locations, and the atmospheric pressure has been increased enough by greenhouse gas injection and biological gas exchange to allow liquid water to be stable at the surface, engineered pioneer plants can be introduced. The mycorrhizal associations of these pioneer plants must be pre-established. The plant seeds are coated with the specific fungal strains needed for their mycorrhizal associations, so that the mycorrhizal network is established immediately upon germination, rather than requiring the plant to search for compatible fungi in the sparse and unfamiliar Martian fungal community. The pioneer plant-fungal partnerships are designed as complete mini-ecosystems. Each plant species brings its specific mycorrhizal partners, nitrogen-fixing bacterial associates, and rhizosphere microbial communities, creating a package that establishes a functional mini-ecosystem at each planting location, rather than a single plant struggling in isolation. Stage 4, planetary network expansion. As pioneer plant fungal communities establish and expand across the Martian surface over centuries, the mycorrhizal networks of adjacent communities begin to contact and merge, exactly as they do during forest succession on Earth. The merger of networks creates connections between plant communities that enable resource sharing across the gaps between established communities, accelerating colonization of the intervening bare regolith. The expanding network is not simply spreading, it is actively engineering the environments as it expands. The biological processes of the established network, carbon fixation, nitrogen fixation, mineral weathering, water harvesting, organic matter accumulation, change the atmospheric composition, soil chemistry, and microclimate of adjacent areas, making them progressively more hospitable for further colonization. The network is terraforming the planet ahead of its own frontier, preparing the ground for its own expansion. This self-propagating, self-engineering expansion is the key advantage of the biological terraforming approach over purely chemical or mechanical approaches. A chemical greenhouse gas injection program requires constant human management and energy input to maintain. A biological network, once established, maintains and expands itself using solar energy, requiring only occasional guidance rather than constant management. Stage 5, planetary mycorrhizal supernetwork. Within a millennium to several millennia, depending on the rate of atmospheric warming and the genetic engineering of pioneer organisms, the mycorrhizal networks of Mars will have merged into a planetary supernetwork, a continent-spanning interconnected system that integrates every plant community on the planet into a single biological system. This planetary mycorrhizal supernetwork is the biological equivalent of the planetary nervous system, integrating information from every point on the surface, distributing resources from areas of surplus to areas of deficit, coordinating biological responses to planetary-scale environmental changes, and maintaining the homeostatic conditions that the developing biosphere requires. The same electromagnetic coil architecture described in the omega tree system, organized through the planetary mycorrhizal network, generates the distributed magnetic field that protects the developing Martian atmosphere from solar wind stripping, ensuring that the atmospheric gains of biological gas exchange are preserved rather than eroded. Outer solar system and exoplanetary applications. Europa and icy moon applications. The icy moons of the outer solar system, Europa, Enceladus, Titan, present fundamentally different terraforming challenges from Mars. Their potential habitability lies not on their surface, but in the liquid water oceans beneath their ice shells, maintained by tidal heating from their planetary parents. Fungal networks adapted for aquatic environments, specifically marine fungal communities, which are far less studied than soil fungi but represent an enormous diversity of metabolic capabilities, are the appropriate biological foundation for icy moon ecosystems. Marine fungi in Earth's deep ocean already operate under conditions of high pressure, complete darkness, and extreme cold, conditions not entirely unlike the subsurface oceans of Europa or Enceladus. Deploying communities of engineered marine fungi in the subsurface oceans of icy moons, through cryobits that penetrate the ice shell and release biological payloads into the underlying ocean, could initiate the establishment of chemolithotrophic ecosystems powered by the chemical energy of hydrothermal vents, without requiring sunlight or atmospheric modification. These ecosystems would be self-contained, deriving energy from the moon's own geological activity, cycling materials within the ocean volume, and potentially developing significant biological complexity without any terraforming of the surface. Titan's unique potential. Saturn's moon Titan presents the most exotic terraforming opportunity in the solar system, a world with a thick nitrogen atmosphere, lakes and seas of liquid methane and ethane, organic chemistry of extraordinary complexity, and a surface temperature of -179 degrees Celsius. No Earth organism can survive these conditions, but the chemical environment of Titan is rich in the organic molecules that life uses as building blocks, just in forms and at temperatures very different from Earth. Designing fungal systems for Titan would require the most radical biological engineering conceivable. Organisms that use liquid methane as a solvent rather than water, metabolize acetylene as an energy source rather than organic carbon, and build structural molecules from the complex organic polymers, tholins, that Titan's atmosphere produces abundantly from photochemical reactions. This is not an extension of Earth biology but a redesign of it, using the structural and functional principles of life while replacing nearly every specific molecule with Titan-compatible analogs. The fungal network architecture, distributed, resilient, resource-sharing, intelligence distributing, is the right architecture for Titan colonization precisely because it is robust to extreme conditions, capable of establishing in resource-poor environments, and able to create biological complexity from simple chemical feedstocks. The specific chemistry must be redesigned, but the network principle transfers. The fungal civilization, a society built on network intelligence, rethinking civilization through the fungal lens. The deepest implication of the fungal network as a civilizational model is not technological, it is philosophical. It proposes a fundamentally different answer to the question of how complex systems should be organized. Industrial civilization is organized on a hierarchical, centralized model, a command structure with central decision-making, standardized products, homogeneous processes, and linear flows of materials and information. This model is efficient for simple, stable, high-volume tasks, manufacturing standardized goods, transmitting information at high speed, but brittle in the face of disruption, destructive of the diversity that enables adaptation, and incapable of the self-repair and self-organization that long-term resilience requires. The fungal network model is the opposite, distributed, decentralized, heterogeneous, and adaptive. Decision-making is local, at every point in the network simultaneously, based on local information and local conditions. No central node controls the network, its behavior emerges from the interactions of millions of individually simple components following local rules. Resources flow toward where they are needed, rather than where centralized planning directs them. Disruption at any point is absorbed by the network's redundancy, alternative pathways carry the load while the disrupted section regenerates. A civilization organized on fungal network principles would be distributed, manufacturing, food production, energy generation, water management, and information processing distributed across millions of local nodes rather than concentrated in central facilities. Each node self-sufficient and connected to the network, contributing surplus to the network while drawing on the network's resources when locally depleted. Adaptive, continuously reorganizing in response to changing conditions, with resources and capabilities flowing toward emerging needs and away from declining ones. The reorganization is not directed by central planning but emerges from the network's response to local signals, exactly as a mycorrhizal network reorganizes its hyphal architecture in response to the changing resource landscape of the soil. Regenerative, producing no net waste, with the outputs of every process feeding into other processes in continuous cycles. The network model is inherently circular because every point in the network is simultaneously a producer and consumer, taking from the network while contributing to it, exactly as every organism in an ecosystem is simultaneously a producer and consumer of the ecosystem's material and energy flows. Resilient, robust to disruption, climate variability, and the inevitable surprises of long-term operation. The redundancy built into network architectures, multiple pathways for every resource flow, multiple nodes capable of every function, means that no single disruption can catastrophically impair the system. The network degrades gracefully under stress and regenerates rapidly when stress is relieved. Intelligent, capable of learning, memory, and adaptive response at the network level, beyond what any individual node can achieve. The collective intelligence of a well-connected network, processing information from millions of local sensors and coordinating responses responses across millions of nodes, is qualitatively different from and superior to the intelligence of any centralized decision-making system. The fungal network as governance model. Indigenous governance systems, particularly those of forest-dependent peoples who lived within and managed mycorrhizal connected forest ecosystems for millennia, reflect the principles of the fungal network in their social organization. Decisions made by consensus, resources shared according to need, knowledge distributed through community rather than concentrated in specialists, authority decentralized and contextual rather than centralized and hierarchical. These are the social expressions of the same principles that govern fungal network organization. The transition to a sustainable society is not just a technological transition, it is a governance transition, from the centralized, hierarchical, short-term oriented governance of industrial civilization to the distributed, adaptive, long-term oriented governance of a network civilization. The fungal network is both a model and a metaphor for this transition, showing, in biological terms, what governance structures capable of managing complex systems across long timescales look like in practice. The unified vision. From spore to star, the journey we have traced in this conversation, from a single fungal spore and degraded soil to a planetary civilization managing multiple terraformed worlds, is not a fantasy. It is a sequence of achievable steps, each building on the last, each enabled by the same fundamental principles that have governed life on Earth for billions of years. The fungal network is not a technology we have invented. It is a technology that life invented, the most sophisticated distributed resource management and intelligence system in the history of Earth, operating for 450 million years with perfect sustainability, zero waste, and continuous adaptive improvement. Our task is not to invent a replacement for this system. Our task is to understand it deeply enough to work with it, to extend its reach, amplify its capabilities, and direct its extraordinary powers toward the regeneration of our damaged planet and the extension of life beyond it. Every action in this direction, restoring a mycorrhizal network in a degraded field, connecting a forest fragment through a fungal corridor, incorporating mycelium materials into a building, studying the intelligence of a fungal network, protecting the biodiversity of the fungal kingdom, learning from indigenous peoples who have lived in partnership with these networks for generations, is simultaneously an act of Earth regeneration, a step towards sustainable civilization, and a contribution to the cosmic project of extending life across the universe. The universe is 13.8 billion years old. Life on Earth is 3.8 billion years old. Complex multicellular life is 600 million years old. Mycorrhizal networks are 450 million years old. Human civilization is 10,000 years old. The transition to sustainable civilization is decades old. We are at the very beginning of understanding what life can do, and the fungal network, running silently beneath our feet across every continent, is one of the oldest and wisest teachers we have. The path to the stars runs through the soil. It always has. Underground fungal networks, especially mycorrhizal networks, could become one of the most powerful biological foundations for a regenerative civilization because they represent a natural communication, nutrient, and energy-sharing system that has supported ecosystems for hundreds of millions of years. They cannot single-handedly regenerate Earth or terraform planets, but when combined with ecological restoration, advanced technology, renewable energy, synthetic biology, and sustainable human systems, they could become a central component of a planetary-scale regeneration strategy. The vision would be to create a planetary fungal ecological infrastructure, a living network of forests, fungi, plants, microbes, wetlands, and human technologies that restores damaged ecosystems on Earth and provides biological foundations for future extraterrestrial environments. Understanding the power of underground fungal networks. Fungi form vast underground structures called mycelial networks. These are microscopic threads that spread through soil and connect plants together. A single fungal network can transport nutrients between plants, help plants access water and minerals, store carbon in soils, improve soil structure, increase plant resistance to drought and disease, accelerate ecosystem recovery, support biodiversity. Many fungi form partnerships with plant roots called mycorrhizae. The plant provides fungi with sugars produced through photosynthesis, while fungi provide minerals such as phosphorus, nitrogen compounds, and water. This creates a natural cooperation system. Plants provide energy, fungi distribute resources, ecosystems become more resilient. A sustainable civilization could learn from this principle by designing human systems around cooperation rather than extraction, regenerating damaged soils through fungal restoration. One of the largest challenges on Earth is degraded soil. Industrial agriculture, deforestation, mining, and pollution have destroyed many soil ecosystems. A global fungal regeneration program could include mycorrhizal restoration. Scientists and restoration teams could introduce native fungal species into damaged ecosystems to help plants establish themselves. Examples: desert restoration projects could combine drought-resistant plants with fungi that improve water absorption. Former agricultural land could be converted into regenerative forests supported by underground fungal networks. Mining areas could be restored using fungi capable of helping plants grow in contaminated soils. The goal would be to transform dead soil into living soil. A healthy ecosystem is not simply a collection of plants, it is a complex underground civilization of microbes, fungi, roots, and organisms, creating global fungal forest networks. A regenerated Earth could contain interconnected ecological zones, production rainforests. Instead of destroying forests for agriculture and industry, humanity could create production forests that produce food, medicines, biomaterials, natural chemicals, fibers, renewable fuels, carbon storage. These forests could use fungal networks to maintain productivity without artificial fertilizers. A production rainforest could contain fruit trees, nut trees, bamboo, medicinal plants, nitrogen-fixing plants, pollinator habitats, mycorrhizal fungi, wetland systems. The forest itself becomes a living factory, using fungi to replace destructive industries. Fungal biotechnology could help create a circular economy. Sustainable materials. Mycelium can be grown into materials such as packaging, insulation, building materials, leather alternatives, lightweight composites. Instead of extracting petroleum to create plastics, society could grow materials using biological processes. Pollution cleanup. Some fungi can perform mycorremediation, where they help break down pollutants. Potential applications: cleaning oil-contaminated soils, removing certain industrial chemicals, supporting ecosystems around polluted areas, helping restore damaged waterways. Waste transformation. A fungal circular economy could transform organic waste into soil amendments, fertilizer alternatives, biomaterials, mushroom-based foods. The ideal system would imitate forests. Nothing is waste, everything becomes a resource, creating fungal-powered regenerative agriculture. Current agriculture often separates crops from ecosystems. A fungal-based agricultural civilization would function more like a natural forest. A regenerative farm could include agroforestry. Trees, crops, fungi, animals, and microbes work together. Examples: fruit trees over vegetables, nitrogen-fixing plants improving soil, fungal networks distributing nutrients, wetlands filtering water, pollinator habitats supporting reproduction, food forests. Instead of annual monocultures, cities and rural areas could develop permanent edible ecosystems. A food forest could provide fruits, vegetables, nuts, herbs, mushrooms, medicinal plants. Fungi would help maintain fertility naturally, building fungal integrated sustainable cities. Future cities could become ecological organisms. A fungal-based city could include living infrastructure. Buildings could incorporate mycelium insulation, plant-covered surfaces, biological water systems, urban forests, soil ecosystems, underground ecological networks. Beneath cities, fungal gardens, root systems, water storage, microbial ecosystems. These could help regulate temperature, flooding, pollution, carbon storage. A future city could function more like a rainforest than a machine. Combining fungi with advanced technology. Fungi alone cannot solve all environmental problems, but they could work together with advanced technologies. Artificial intelligence. AI could monitor soil health, fungal biodiversity, carbon storage, water cycles, forest regeneration. AI systems could optimize ecosystems similarly to how a forest naturally balances itself. Sensors and biotechnology. Networks of environmental sensors could measure moisture, nutrient levels, microbial activity, plant health. Robotic systems could assist restoration by planting native species and supporting ecosystem recovery. Renewable energy. Regenerative ecosystems would be powered by solar energy, wind energy, geothermal energy, ocean energy. Clean energy would power restoration without increasing ecological damage, creating a planetary-scale fungal restoration network. A possible Earth regeneration strategy. Phase 1. Restore soil. Map damaged ecosystems. Reintroduce native fungi. Restore microorganisms. Stop soil erosion. Phase 2. Restore forests. Plant native forests. Create wildlife corridors. Expand wetlands. Protect biodiversity. Phase 3. Create regenerative economies. Replace destructive industries with biomaterials, regenerative agriculture, circular manufacturing, renewable energy. Phase 4. Connect ecosystems. Create ecological corridors across continents, forest networks, river restoration systems, wildlife migration routes, fungal-rich soils. The planet becomes a connected living system. Using fungal networks for space colonization and terraforming, fungi could become important in future extraterrestrial ecosystems because they are extremely adaptable organisms. However, true terraforming would require enormous technological advances and centuries or longer. A realistic approach would begin with controlled habitats, lunar habitats. On the moon, fungi could potentially help within sealed environments by recycling organic waste, supporting plant growth, creating biological materials, helping maintain closed ecosystems. Mars habitats. Mars presents challenges: extreme cold, low pressure, radiation, toxic soil chemicals, lack of liquid water, Fungal systems could potentially assist inside protected environments by breaking down waste, creating soil-like materials, supporting greenhouse ecosystems, helping plants grow. A future Martian ecosystem might contain underground fungal networks, engineered soils, greenhouses, artificial wetlands, algae and plant systems, engineering planetary mycelium systems. A futuristic concept would be a planetary biological infrastructure inspired by fungal networks. It could include ecological networks, Earth, forests, wetlands, grasslands, coral ecosystems, Mars, underground habitats, artificial soils, controlled biological ecosystems, information networks, fungal communication inspires, distributed AI, self-organizing systems, biological computing concepts, resource networks, like fungi distribute nutrients, civilization could distribute energy, materials, knowledge, food. The principle becomes, a healthy planet is not a collection of isolated parts, it is a connected living network. The ultimate vision, a fungal-inspired civilization. The most sustainable civilization would imitate a forest. A forest produces oxygen, stores carbon, creates food, purifies water, builds soil, supports biodiversity, uses renewable energy from sunlight. A fungal-inspired human civilization would restore ecosystems instead of destroying them, grow materials instead of extracting them, recycle everything, use renewable energy, protect biodiversity, integrate technology with biology. Earth could become a thriving planetary garden, and future worlds could be transformed from barren environments into carefully designed living ecosystems. The deepest lesson from fungi is that survival does not come from domination, but from connection, cooperation, and the intelligent sharing of resources. A civilization built around these principles could potentially regenerate Earth and provide the foundation for humanity's expansion into space. The fungal civilization, regenerating Earth and building sustainable worlds through underground networks, learning from the hidden intelligence beneath our feet. Beneath forests, grasslands, and even degraded landscapes exists one of the most important biological systems on Earth, underground fungal networks. These vast networks of microscopic threads, called mycelium, connect plants, transport nutrients, store carbon, improve soils, and help ecosystems survive environmental challenges. Although fungi alone cannot solve every planetary problem, they represent a powerful model for creating a future civilization that works in harmony with natural systems. For millions of years, fungi have acted as Earth's recyclers, communication systems, and ecological engineers. They transform dead organic matter into nutrients, support plant communities, and maintain the balance of ecosystems. By studying and expanding these natural processes, humanity could develop regenerative systems that restore damaged environments, replace destructive industries, create sustainable cities, and eventually support biological habitats beyond Earth. A future based on fungal principles would not attempt to dominate nature. Instead, it would cooperate with natural processes and combine them with advanced technologies such as artificial intelligence, biotechnology, renewable energy, robotics, and ecological engineering. The result could be a planetary civilization where human activity actively restores the environment rather than degrading it. The foundation of ecosystems, the power of mycelial networks. Fungi are among the oldest and most adaptable organisms on Earth. Their underground structures, known as mycelial networks, consist of countless interconnected fungal threads called hyphae. These networks can spread through enormous areas of soil and interact with plants, microorganisms, and minerals. One of the most important relationships in nature is the partnership between fungi and plant roots, known as mycorrhizal symbiosis. In this relationship, plants provide fungi with sugars created through photosynthesis, while fungi help plants obtain essential resources. The fungal network acts as a biological transportation system. It can move water from areas of greater availability to areas of scarcity, minerals from soil particles into plant roots, carbon compounds between organisms, chemical signals that influence plant responses. This means that forests are not simply collections of individual trees. They are interconnected communities where plants, fungi, and microorganisms cooperate. This principle provides a powerful lesson for human civilization. Resilience comes from connection and cooperation rather than isolation. Restoring Earth's soils through fungal regeneration. One of the greatest environmental challenges today is soil degradation. Industrial agriculture, deforestation, mining, and pollution have damaged soil ecosystems around the world. When soils lose organic matter and microbial life, they become less capable of supporting plants, storing carbon, and retaining water. A global fungal restoration effort could help rebuild these damaged landscapes. Healthy fungal networks can improve soils by increasing organic matter, creating stable soil structures, improving water retention, supporting plant growth, increasing resistance to drought, helping ecosystems recover after disturbances. Instead of viewing soil as a simple material for growing crops, humanity could begin treating soil as a living ecosystem. Restoration programs could introduce native fungal communities alongside native plants to rebuild damaged environments. Forests, grasslands, wetlands, and agricultural landscapes could gradually recover as underground biological networks return. Fungal networks in the fight against desertification. Desertification is one of the most serious ecological challenges facing many regions. When vegetation disappears, soil becomes exposed to wind and erosion, causing landscapes to lose their ability to retain water and support life. Fungal networks could become an important part of large-scale desert restoration. A fungal-based desert regeneration system could combine native drought-resistant plants, mycorrhizal fungi, rainwater harvesting, soil-building organisms, wind protection systems, regenerative agriculture. The first plants introduced into degraded deserts would act as ecological pioneers. Their fungal partners would help them survive harsh conditions, allowing more species to establish themselves over time. Eventually, some desert regions could transform into more productive ecosystems, such as grasslands, shrublands, agroforestry systems, forest ecosystems where climate conditions allow. The goal would not be to artificially turn every desert into a rainforest, but to restore natural ecological balance and increase biological productivity, creating global production rainforests. One of the most revolutionary applications of fungal ecology would be the development of production rainforests. Modern civilization often separates agriculture, industry, and ecosystems. Forests are destroyed to create farms, and resources are extracted through mining and drilling. A production rainforest would reverse this approach by creating ecosystems that produce resources while becoming healthier over time. A production rainforest could provide food, medicine, natural fibers, biomaterials, renewable chemicals, carbon storage, wildlife habitat. These systems would imitate natural forests by using multiple ecological layers. The upper canopy could contain large trees producing fruits, nuts, oils, and carbon storage. The middle layers could contain shrubs and smaller trees producing food, medicine, and fibers. The ground layer could contain vegetables, herbs, fungi, and soil-building plants. The underground layer would contain extensive fungal networks maintaining nutrient cycles. Instead of factories that consume resources and create pollution, production rainforests would function like living factories that regenerate their environment, replacing destructive industries with fungal biotechnology. Fungi could also contribute to replacing many environmentally harmful materials and processes. Mycelium-based materials. Mycelium can be grown into strong, lightweight materials. These materials could replace some petroleum-based products. Possible applications include packaging, building insulation, furniture materials, leather alternatives, composite materials. Instead of extracting fossil resources, humanity could grow materials through biological processes. Fungal waste recycling. Natural ecosystems have no concept of waste. Everything becomes a resource for another organism. A fungal circular economy could transform waste into useful products. Organic waste could become soil amendments, mushroom production, biomaterials, compost, nutrient sources. This would help humanity move away from a linear economy based on extraction, consumption, and disposal, using fungi to clean polluted environments. Fungi are also valuable environmental restoration tools because some species can break down complex compounds through specialized enzymes. This process, called mycorrhization, could help restore polluted areas. Potential applications include cleaning contaminated soils, restoring damaged industrial sites, supporting polluted waterways, helping ecosystems recover after chemical contamination. Future restoration systems could combine fungi with bacteria, plants, artificial intelligence, environmental sensors. These systems could become living pollution treatment networks. Regenerative agriculture based on fungal cooperation. A sustainable food system would need to move beyond industrial monocultures toward ecosystems that function more like natural forests. Regenerative fungal agriculture could combine agroforestry, permaculture, food forests, native plants, compost systems, biological soil management. Food forests are especially powerful because they create permanent ecosystems that produce food while improving the environment. A mature food forest could provide fruits, nuts, vegetables, mushrooms, herbs, medicinal plants. Fungal networks would help maintain fertility naturally, reducing dependence on synthetic fertilizers. Agriculture would become a process of ecological partnership rather than environmental extraction, building cities inspired by fungal networks. Future cities could also adopt fungal principles. Instead of cities being isolated from nature, they could become integrated ecological systems. A fungal-inspired city could include urban forests, green roofs, wetlands, community gardens, living buildings, biological water systems. Buildings could incorporate sustainable materials such as mycelium composites and plant-based materials. Underground systems could support soil ecosystems, water management, carbon storage, urban agriculture. The city itself could behave like an ecosystem, with resources continuously recycled and reused. Combining fungal networks with advanced technology. The greatest potential would come from combining biology with advanced technology. Artificial intelligence. AI could help manage planetary restoration by analyzing climate data, soil conditions, biodiversity patterns, carbon storage, ecosystem health. AI could identify where restoration efforts would have the greatest impact. Environmental sensors, networks of sensors could monitor soil moisture, nutrient availability, pollution levels, microbial activity. This would allow restoration teams to understand ecosystems in real time. Robotics, autonomous machines could help restore ecosystems by planting native species, distributing fungal inoculations, monitoring forests, removing invasive species. Technology would become a partner supporting natural regeneration, creating a planetary fungal restoration network. A global regeneration effort could follow several stages. Stage 1. Protect existing ecosystems. The first priority would be protecting remaining, ancient forests, wetlands, grasslands, oceans, biodiversity hotspots. Existing ecosystems are the foundation of planetary health. Stage 2. Restore damaged areas. Humanity could restore degraded lands through native plant restoration, fungal reintroduction, soil rebuilding, water cycle restoration. Stage 3. Connect ecosystems. Large ecological corridors could reconnect fragmented habitats. These corridors would allow wildlife movement, genetic diversity, climate adaptation. Stage 4. Transform civilization. Human industries would transition toward renewable energy, circular manufacturing, regenerative agriculture, sustainable materials. Humanity would become a restoration force, using fungal systems beyond Earth. The same ecological principles could eventually help humanity create sustainable habitats in space. Terraforming entire planets remains far beyond current capabilities, but controlled biological ecosystems are a realistic first step. Moon habitats. The moon lacks a breathable atmosphere, liquid surface water, natural ecosystems. Fungi could help inside sealed habitats by recycling organic waste, producing biological materials, supporting plant growth systems. Mars habitats. Mars presents even greater challenges: extreme cold, radiation, thin atmosphere, toxic soil chemicals. Future Martian habitats could use underground environments protected from radiation. Fungal systems could contribute by creating biological recycling systems, helping produce artificial soils, supporting greenhouse ecosystems, producing useful materials. Over long periods, biological systems could gradually transform controlled environments into more Earth-like ecosystems. A future fungal civilization. The ultimate lesson of fungi is that life thrives through relationships. A fungal-inspired civilization would recognize that forests are not just resources, they are living systems. Soil is not dirt, it is a biological community. Waste is not useless, it is a resource. Technology should support ecosystems rather than replace them. Human prosperity depends on planetary health. Such a civilization would combine the intelligence of nature with the creativity of humanity. Earth could become a regenerated planet covered with connected forests, healthy soils, clean waterways, sustainable cities, and abundant biodiversity. Humanity could eventually carry these principles beyond Earth, creating habitats that respect ecological balance. The future may not be defined by humanity conquering nature, but by humanity learning from nature. Like the fungal networks beneath the forest floor, civilization could become a connected living system where every part supports the health of the whole. How can we increase sustainability of human society every year with this? How humanity could increase sustainability every year through fungal networks and regenerative systems. A truly sustainable civilization would not aim to reach a fixed level of sustainability and stop. It would continuously improve every year, similar to a natural ecosystem. Forests become richer over time because plants, fungi, animals, and microorganisms constantly build soil, recycle nutrients, increase biodiversity, and adapt to changing conditions. By using underground fungal networks as a biological model, humanity could create a society that becomes progressively more regenerative each year. The goal would be to design systems where every decade produces more forests, healthier soils, cleaner energy, greater biodiversity, and more efficient resource cycles than the decade before. Creating a yearly planetary regeneration cycle, humanity could establish a global ecological improvement system where every year the planet becomes healthier. Instead of measuring success only through economic growth, societies could measure increase in forest coverage, increase in soil carbon, increase in biodiversity, reduction in pollution, reduction in resource consumption, improvement in ecosystem health, increase in renewable energy, increase in circular production. Each year, governments, communities, and industries could set higher ecological goals. For example, Year 1, restore degraded soils, expand renewable energy, protect ecosystems. Year 10, restore millions of hectares of forests, replace many fossil-based industries, create circular manufacturing systems. Year 50, establish globally connected ecological networks, operate mainly on renewable resources, maintain a climate-positive civilization. The planet would continuously move toward greater health, expanding global fungal soil networks every year. One of the most important strategies would be increasing the amount of healthy, living soil. Every year humanity could restore more degraded farmland, increase fungal diversity, plant more native vegetation, expand regenerative agriculture, increase organic matter in soils. Farmers could use fungal supporting practices such as reducing soil disturbance, planting diverse crops, growing cover crops, adding compost, integrating trees into agricultural landscapes. Over time, agricultural land would become more like a living ecosystem. Instead of soils becoming exhausted every year, they would become more fertile, expanding regenerative forests every year. A fungal civilization would continuously increase forest ecosystems. Every year, humanity could expand native forests, food forests, agroforestry systems, urban forests, wildlife corridors. Each restored forest would create additional carbon storage, habitat, rainfall regulation, soil improvement, water filtration. The forests themselves would help create conditions for more forests by improving local climates and water cycles. This creates a positive feedback loop: more forests, healthier soils, stronger fungal networks, more plant growth, more forests, creating self-improving regenerative agriculture. Agriculture could become more sustainable every year by functioning like an ecosystem. Traditional agriculture often follows plant harvest, remove nutrients, add external inputs. A regenerative fungal-based system follows plant harvest, recycle nutrients, improve soil, increase productivity. Each year, farms could increase soil fertility, carbon storage, biodiversity, water efficiency, crop diversity. Future farms could combine food forests, mushroom cultivation, fungal soil systems, vertical farming, solar energy, water recycling. The farm would become more productive while becoming more environmentally valuable. Building cities that become greener every year. Cities could be designed like ecosystems that improve with time. Each year, cities could increase urban forests. More trees would provide cooling, carbon storage, cleaner air, wildlife habitat, green infrastructure. Cities could expand green roofs, living walls, rain gardens, wetlands, natural drainage systems, biological materials. More buildings could use mycelium materials, plant-based composites, recycled materials, carbon-storing materials. A sustainable city would not remain static. It would become greener, cleaner, and more efficient every year, creating a circular economy inspired by fungi. Fungi demonstrate perfect recycling. A dead tree does not become waste. Fungi transform it into nutrients that support new life. Human society could imitate this. Every year, economies could increase material recycling, product reuse, biological manufacturing, composting, waste reduction. Industries could transition from linear economy, extract, manufacture, consume, discard, to circular economy, grow, use, recycle, regenerate. Eventually, most materials could continuously circulate through society, replacing fossil fuels with regenerative energy systems. Fungal ecosystems run on renewable energy from the sun. Human civilization could do the same. Each year, society could increase solar energy, wind energy, geothermal energy, ocean energy, advanced energy storage. Energy systems could become increasingly cleaner, more distributed, more efficient. Renewable energy could power restoration robots, sustainable factories, electric transportation, water purification, climate adaptation systems. Clean energy would become the foundation for ecological regeneration. Using AI to optimize planetary sustainability, artificial intelligence could become a planetary management assistant. AI systems could analyze climate patterns, ecosystem health, soil conditions, water availability, biodiversity changes. Every year, AI could improve restoration strategies by learning from previous results. For example, a restoration project might discover that certain fungal species work best with specific native plants in a particular climate. AI could use this knowledge to improve future projects. This would create a continuously learning ecological civilization, creating biological manufacturing systems. Future industries could increasingly behave like ecosystems. Instead of factories that create pollution, humanity could create biological production systems. Examples include fungal manufacturing, producing, packaging, materials, chemicals, plant-based manufacturing, producing, fibers, medicines, food ingredients, algae systems, producing, fuels, materials, carbon capture. Each year, these systems could become more efficient through research and biotechnology, increasing biodiversity every year. A sustainable planet is not only carbon neutral, it is biologically rich. Every year, humanity could increase biodiversity through restoring habitats, creating wildlife corridors, protecting endangered species, expanding native ecosystems. Fungal networks would support this by creating healthier soils capable of supporting more plant and animal species. A biodiversity increase creates stronger ecosystems that are more resistant to climate change, disease, extreme weather, creating regenerative education systems. Long-term sustainability requires cultural transformation. Every generation could learn ecology, regenerative agriculture, renewable energy, circular economics, conservation, biomimicry. Schools could include forest gardens, community farms, ecological restoration projects, sustainability laboratories. Human knowledge would grow alongside ecological knowledge, establishing a global planetary immune system. Fungal networks can be compared to the immune system of forests because they help ecosystems respond to stress. Humanity could create a planetary ecological monitoring network using satellites, AI, sensors, biological indicators. This system could detect deforestation, pollution, species decline, soil degradation. Problems could be addressed before they become global crises, expanding beyond Earth. The same principles could guide future space settlements. A sustainable extraterrestrial civilization would require closed-loop ecosystems where waste becomes nutrients, plants produce oxygen, fungi recycle materials, microorganisms maintain soil, energy comes from renewable sources. Future Moon or Mars habitats could improve every year by increasing biological diversity, recycling efficiency, food production, ecosystem stability. They would grow like artificial forests inside protected environments. The ultimate goal, a civilization that becomes more alive every year. The most sustainable society would not simply reduce harm, it would actively create more life and abundance every year. A fungal-inspired civilization would follow these principles: more forests every year, more biodiversity every year, healthier soils every year, cleaner energy every year, less waste every year, better technology every year, greater cooperation every year. Instead of a civilization that consumes the planet, humanity could become a planetary regeneration system. The future could resemble a giant ecological network, forests acting like lungs, rivers acting like circulation systems, fungal networks acting like communication and nutrient systems, renewable energy acting like biological sunlight, human technology acting like a supportive nervous system. By continuously learning from fungi and ecosystems, humanity could create a civilization that does not merely survive on Earth but helps Earth become healthier, richer, and more resilient with every passing year. The ever-regenerating civilization, increasing human sustainability every year through fungal networks and nature-inspired systems. From sustainable to regenerative civilization, humanity has traditionally organized its societies around extraction. Forests are cut for materials, soils are depleted for agriculture, fossil fuels are burned for energy, and waste is often discarded after use. While sustainability attempts to reduce environmental damage, the next stage of human development could be regeneration, creating a civilization that improves the health of the planet every year. Nature provides a powerful model for this transformation. In forests, underground fungal networks connect plants, recycle nutrients, build soils, store carbon, and strengthen ecosystems. Fungi demonstrate a fundamental principle of life. Long-term prosperity comes from cooperation, circular resource flows, and interconnected systems. By applying the principles of fungal networks to human civilization, humanity could create a society that continuously becomes more sustainable. Each year could bring more forests, healthier soils, cleaner energy, greater biodiversity, more efficient technologies, and stronger ecological systems. The ultimate goal would be a civilization that functions like a living ecosystem, one that does not simply avoid harming Earth but actively restores and enriches it. The fungal network as a model for human civilization. Fungal networks are among the most sophisticated natural systems on Earth. Beneath forests, billions of fungal threads form interconnected webs that allow plants and microorganisms to exchange resources and information. A forest does not operate as a collection of isolated individuals. Instead, it functions as a cooperative community. Trees provide fungi with carbon-rich sugars produced through photosynthesis. In return, fungi help trees obtain water and minerals from the soil. Fungi also break down dead organic material, returning nutrients to the ecosystem. This creates a continuous cycle: growth, cooperation, recycling, regeneration, greater growth. A sustainable human civilization could follow the same principle. Instead of extraction, production, consumption, waste, society could move toward renewable resources, circular production, reuse, regeneration. The fungal network becomes a blueprint for designing economies, cities, agriculture, and technologies that become healthier over time, creating a global soil regeneration movement. Healthy soil is the foundation of civilization. Almost all terrestrial life depends on functioning soils, yet many agricultural lands have lost organic matter, biodiversity, and water-holding capacity. A regenerative civilization would treat soil as a living ecosystem. Every year, humanity could increase soil health through expanding mycorrhizal fungal networks, increasing organic matter, reducing destructive soil disturbance, planting diverse vegetation, restoring microorganisms, preventing erosion. Regenerative farming systems could use fungi as biological partners rather than relying heavily on synthetic fertilizers. Fungal networks would help crops access nutrients more efficiently, survive drought, develop stronger root systems, improve soil structure. Over decades, degraded agricultural land could become increasingly fertile. Instead of farming systems that slowly exhaust the land, agriculture could become a process that continuously improves the earth, expanding forest networks every year. Forests are among the most powerful natural systems for regulating the planet. They capture carbon, influence rainfall, protect biodiversity, and create healthy soils. A regenerative civilization would not simply preserve forests, it would expand and improve them. Every year, humanity could create new native forests, food forests, agroforestry landscapes, urban forests, wildlife corridors, restoration forests. These forests would be connected through underground fungal networks. As forests expand, they would create positive feedback loops. More trees create more organic matter. More organic matter supports more fungi. More fungi improve soil. Better soil supports more plants. More plants support more biodiversity. Over time, ecosystems would become increasingly complex and resilient, building production rainforests as regenerative industries. One of the greatest opportunities for increasing sustainability every year is replacing destructive industries with biological production systems. A production rainforest would function as a living factory. Unlike conventional factories that consume resources and produce pollution, production rainforests would generate valuable materials while improving ecosystems. They could provide food, medicines, natural fibers, biomaterials, renewable chemicals, carbon storage, wildlife habitat. These ecosystems could combine trees, crops, mushrooms, pollinator plants, nitrogen-fixing species, aquatic systems, soil organisms. The productivity of these systems could increase over time because the ecosystem itself becomes healthier. A mature production rainforest could become more valuable every year rather than becoming depleted, transforming agriculture into living ecosystems. Agriculture is one of humanity's largest impacts on Earth. A regenerative future would redesign farming to work more like natural ecosystems. Traditional agriculture often depends on large-scale monocultures, chemical inputs, soil disturbance, external energy. A fungal-based regenerative agricultural system would use agroforestry, permaculture, food forests, biological pest control, compost cycles, mycorrhizal partnerships. A farm could become an ecosystem where every component supports another. For example, trees provide shade and organic matter, plants provide food, fungi distribute nutrients, microorganisms maintain soil health, pollinators support reproduction, water systems maintain stability. Each year, the farm could become more productive and environmentally valuable, developing a circular economy inspired by fungi. One of the greatest lessons from fungi is that nature creates almost no waste. A fallen tree does not become pollution. Fungi transform it into nutrients that support future life. Human society could create a similar circular economy. Every year, industries could increase recycling efficiency, material reuse, biological manufacturing, composting, resource recovery. Future manufacturing systems could use mycelium materials, plant-based materials, algae-based products, recycled metals, regenerative biomaterials. Products would be designed from the beginning for reuse, repair, and recycling. The economy would gradually shift from a system of consumption to a system of continuous renewal, creating cities that become more sustainable every year. Cities are often considered separate from nature, but future cities could become ecological systems. A regenerative city would continuously increase its environmental performance. Each year, cities could add more urban forests, more green roofs, more natural water systems, more renewable energy, more sustainable buildings, more local food production. Buildings could incorporate biological materials such as mycelium composites and plant-based materials. Urban areas could contain community food forests, pollinator habitats, wetlands, ecological corridors. Cities would become places where human life and natural systems coexist. Using artificial intelligence to improve sustainability every year, a regenerative civilization would require constant learning and adaptation. Artificial intelligence could become a powerful tool for managing planetary systems. AI could analyze climate patterns, soil conditions, forest health, biodiversity changes, water systems, pollution levels. Each year, AI systems could improve restoration strategies by learning from previous projects. For example, AI could determine which plants restore a specific ecosystem fastest, which fungal species improve soil in certain climates, where forests should be expanded, how renewable energy systems can become more efficient. Technology would become a partner of ecological intelligence, creating a planetary ecological monitoring system. A healthy planet requires awareness of what is happening everywhere. Humanity could create a global ecological monitoring network using satellites, sensors, artificial intelligence, biological indicators. This system could monitor deforestation, soil degradation, ocean health, biodiversity loss, pollution. Instead of discovering environmental crises after major damage occurs, humanity could respond early. This would function like an ecological immune system for Earth, increasing biodiversity every year. Sustainability is not only about carbon emissions. A truly healthy planet requires biological abundance. Every year, humanity could increase biodiversity by restoring habitats, protecting endangered species, expanding ecological corridors, creating native landscapes, reducing pollution. Fungal networks would support biodiversity by creating healthier soils capable of supporting more species. Biodiversity itself creates resilience. A diverse ecosystem can better withstand climate change, disease, extreme weather, environmental disturbances. A richer natural world creates a stronger civilization, creating renewable energy systems that support regeneration. A regenerative society would require clean energy to power restoration and technology. Every year, humanity could expand solar power, wind power, geothermal energy, ocean energy, advanced energy storage. Renewable energy would support ecological restoration, sustainable transportation, clean manufacturing, water purification, recycling systems. Energy production would become increasingly separate from environmental destruction, expanding regenerative education and culture. Technology alone cannot create a sustainable civilization. Humanity also needs a cultural transformation. Education systems could teach ecology, regenerative design, sustainable engineering, conservation, circular economics, biomimicry. Schools could include forest gardens, restoration projects, sustainability laboratories, community agriculture. Each generation would become better equipped to improve the planet. Knowledge itself would become a regenerative resource. Applying fungal principles to space exploration, the same principles could eventually guide humanity beyond Earth. Future Moon and Mars habitats would require closed ecological systems where resources are continuously recycled. Fungi could help create these systems by recycling organic waste, supporting plant growth, producing biological materials, maintaining soil-like environments. A future space settlement could operate like a miniature forest. Plants produce oxygen and food. Fungi recycle nutrients. Microorganisms maintain ecological cycles. Technology provides energy and protection. Over time, these systems could become increasingly self-sufficient. The long-term vision, a civilization that improves forever. The ultimate goal is not merely achieving sustainability. It is creating a civilization that continuously regenerates. Every year, humanity could aim for more forests than before, more biodiversity than before, healthier soils than before, cleaner energy than before, less waste than before, more efficient technologies than before, stronger ecological connections than before. Like a fungal network, civilization would become stronger through cooperation. Humanity would no longer be a force that extracts from the planet. It would become a planetary caretaker system that supports life, becoming the mycelium of Earth. Underground fungal networks teach humanity a profound lesson. Life succeeds through connection. A forest survives because every organism contributes to the health of the whole. A future civilization could follow the same pattern by connecting technology, ecology, and human creativity. Through fungal-inspired systems, humanity could create regenerative agriculture, living cities, circular economies, renewable energy networks, restored ecosystems, sustainable space habitats. The future of sustainability is not a final destination. It is a continuous process of improvement. A truly advanced civilization would not ask, how much can we take from Earth? It would ask, how much life, diversity, and abundance can we create every year? By following the principles of fungal networks, humanity could transform Earth into a thriving planetary ecosystem and eventually carry these regenerative principles to new worlds.